So, my name is Bill Buchanan, and I lead a podcast series on the world leaders in cryptography. And I'm so happy to have a true world leader with me today, and that's Jonathon Katz. Hi, Jonathon.
Hi, how are you?
Jonathon was a professor in the Department of Computer Science at the University of Maryland. He is now a senior staff research scientist at Google and with a core focus on cryptography and cybersecurity. Jonathon received his BS degree in mathematics and chemistry from MIT in 1996, and in 2002 completed a PhD in computer science within Columbia University. He wrote a classic textbook on cryptography, and which is now in its third edition. Jonathon has also created an online course on Coursera and has given tutorials of various forms on different topics to multiple audiences. So, what's your current role and what does a typical day involve for you?
So my current role, as you said, is as a senior staff research scientist at Google. I just began working there about a year and a half ago. I took a leave of absence from the university to start working there, and then just recently, a couple months ago, actually, decided to leave the university and begin working there full time. So there, I'm on a larger team that works on privacy, safety, and security within Google. The team as a whole has many different focuses, not only cryptography, but I'm working primarily with a smaller group within that team doing cryptography. And I guess a typical day for me it really varies. I don't know if there is a typical day. I think generally I'll start by going through my email. I get tons of emails, I'm sure many other people do. But I'm checking about three different email addresses, and I'm getting email from people all over the world in different time zones. So often I'm communicating or working on something a little bit asynchronously. And so I'll check my inbox that morning and respond to whatever I need to respond to there. Um, and then most of the workday itself is focused on reading and writing, where the balance, shifts a bit depending on whether I'm actively writing a paper or whether I'm sort of more in an exploratory mode and working on a problem. I do a lot of reading, reading papers that come out, reading papers that are relevant to my research, etc. And then beyond that, also obviously meeting with people as well. I mean, one of the aspects I enjoy most about the job is the ability to collaborate with people, both within and outside of Google. And so setting up various meetings with people in different time zones is also sometimes challenging, but yeah, a lot of collaborative meetings during the day as well.
Great. So, what were your school days like? What were you like as a pupil?
Well, yeah, that's interesting. Also, because as you mentioned at the beginning of the podcast, I came at cryptography from a bit of a convoluted path. So when I was an undergraduate, I was focusing primarily on chemistry, but I also was really interested in mathematics. So I ended up double majoring in both chemistry and mathematics. And then I actually went on to begin graduate school in chemistry. And after a couple of years in that program, I just found I didn't like it as much as I did as an undergraduate. And really, for me, I think what it was is that I really enjoyed the sort of theoretical aspects of chemistry, and I didn't enjoy as much the hands-on experimental aspects of chemistry. Which, if you've ever done an experimental physical science, you probably know what that can be like. And so um, I started exploring different possibilities. And because of my interest in mathematics, I was looking for something, some field related to mathematics, and I really just hit upon cryptography by I would say luck and good fortune. My only real knowledge of cryptography was from what I had read in the news at that time. There were occasional articles about cryptography then, not nearly as many as there are now. But I thought that it would be a field that would offer a good blend of theory, a good blend of mathematics, but also have real world applications, which was something I was looking for because I really didn't think I would enjoy pure mathematics either. I really wanted something that would have a connection with reality. And I was fortunate then that I was at Columbia University then already for the chemistry PhD, and I was fortunate that there was somebody in the computer science department, Moti Young, who was willing to take me on as an advisee. And yeah, I just got into it from there, and I really fell in love with the field as a whole, and have been fortunate to continue working on it since then.
Yeah, I spoke to Moti. He's such an inspirational
Oh, has he been
person.
on this
Yeah,
podcast before? Yeah,
such a great mentor
yeah,
and
yeah.
such depth of experience. I asked him so many on so many topics, and even though he wasn't maybe the first author on some of the papers, he knew exactly what was going on. So he's a really inspirational researcher and still doing great, really
Yeah, he's
amazing
actually at
work.
Google. He's on my
Yeah,
he's one of the
that's right.
members of the team at Google, so I see him there as well. Everything's come full circle.
So it does seem to be a tract for many people in cryptography to go into industry to have one foot in one camp and one in the other. So
Yeah,
why did you
it's
decide
really
to jump?
well, it's really interesting. I think especially nowadays, I see so many people, and I was just talking about this with somebody recently, that there are so many now what I would call academic or formerly academic cryptographers who have moved into industry, especially in the startup space.
Yeah,
I think over the past, things have changed. Things have shifted from where they were 20 or 30 years ago. 20 years ago, things were dominated by the larger companies, Microsoft, Google, Apple. Although back then, not all of those had large cryptography research teams. But the point is, IBM comes to mind, right? IBM, another large company that had a great cryptography research team. But now, the landscape has shifted, and we have so many startup companies, mainly driven by cryptocurrency, but some also by post-quantum cryptography, or by other aspects of cybersecurity. And there's such an opportunity now for academic cryptographers to go do interesting work in industry. And what's really been surprising to me about all of that is that many of these startup companies are taking ideas that came out of academia. Some of them, have came out in academia 5 or 10 years earlier. And these ideas at the time that they came out were viewed as being pure theory. And I think a lot of times the researcher's motivation for working on the problem was just pure academic curiosity. But then these ideas turned out to have real world applications that these startup companies have taken and started to run with. And so I think that's just been really exciting to watch. And as for why people, or why in my own case, I decided to move from academia to industry, I think there were a lot of factors involved. There was partly, there were things about academia that I was growing tired with, or maybe some of them specific to the University of Maryland. But then also a pull from industry, because I see that in industry, people can do great work and can also have more of an immediate impact. The type
yeah,
of impact you can have in academia, I think, is different from what you can do in industry. They're both important and they can both be gratifying. But for me, I had been in academia about 20 years, and I thought it was time to try something different. I dipped my toes in the water by taking a 2-year leave of absence. The university was nice enough to allow me to take that time. I tried working at a startup company. I enjoyed that really tremendously. I worked there for about a year, and then this opportunity at Google came up, and I took that opportunity, tried that for a year, and really liked it. Really liked the people I was working with. Really liked the ability to impact real world products, and so I decided to stay there.
yeah. I mean, obviously, the US is such a hotbed of cryptography. We have MIT, Stanford, IBM research, I think, was based in New York. There is an ecosystem, I think, either in the East and the West Coast. RSA was obviously, the company was founded through MIT. So in your book writing, so you have uh, a special sort of career which has both research and teaching and book writing, and it's great to see that you write so much. So when it comes to your books, what topics do you find the most interesting to write about?
Well, that's a good question. I think I'd have to think back about it. I think for me, I enjoy the sort of expository writing in general. I think what I tend to enjoy a lot is actually when there is some particular area that I'm less familiar with, and then I need to learn it myself before I can then write about it. And I find for me personally, um, there's something that I really gain actually by doing that because I think in general you oftentimes don't really understand something until you're able to explain it to somebody else. And really being forced to think through some topic, think about different ways of understanding it, different ways of presenting it, is just a really a process that I really tend to enjoy. And so I think for the book in particular, I'm trying to think back because it's been a number of years since I wrote the first edition. But I think what I remember working on and enjoying was some parts related to number theory, just kind of,
Mm.
putting everything in a structure and, things that I picked up bits and pieces here and there and putting it in a linear, structure. And then applying some of that to things like the Payet crypto system. I remember, reading about the Payet crypto system when I was in graduate school. The paper, I believe, if I remember correctly, came out in 1999. And at the time it came out, I think I had trouble maybe following bits and pieces of it or whatever. And then I sort of, a couple of years later, when I was working on the book, thought about it again in the perspective, using some of the number theory and algebra that was already written up in the book. And I kind of, everything kind of clicked, and I came up, with sort of the right way of understanding it, and then being able to put that in the book, I found it, very gratifying. And I've heard actually from a number of people afterward that they sort of appreciated the perspective in the book on that crypto system, and it made it easier for them to understand. So yeah, that may have been my favorite part there.
That's great. I mean, I think you probably find that many people are learning the topic without actually having a formal background in some of the basic principles. They just go straight into public key encryption.
Actually, it's funny that you mentioned that because I think this is, to some extent, I think it may be a problem. I was talking earlier about people working in startup companies, and as one particular example, there's a lot of startup companies nowadays, and a lot of interest nowadays in the general context of concept of zero knowledge proofs and these snarks. And what's really amazing there is you see a lot of what I would call, not maybe this is not their best term, but amateurs, in the sense
Yeah,
of, not that they're not capable or not intelligent, but in the sense that they don't have PhDs in cryptography and they don't have this formal training. And you see also, even at universities, students will be taking courses on zero knowledge proofs without having taken a basic course on cryptography beforehand. Or courses will cover zero knowledge proofs without covering, CBC mode encryption. And it's a little weird. I mean, you can do it, and the techniques are very different. But on the other hand, you're missing a lot of context, and you're also missing this basic idea of proving security. And I think this is a little bit problematic because you see occasionally people will propose schemes that have solid ideas behind them and very innovative ideas behind them, but they don't have a security proof, perhaps. And then you could potentially run into trouble, right? If you don't have a security proof, you're not really sure whether there's some potential flaw or avenue for an adversary to attack. And I guess we haven't yet seen any example that's led to kind of real world attacks on things that have been deployed. But it's probably only a matter of time until that happens. And so I do think people need to also learn the fundamentals as well. I do think that's very important. Yeah.
yeah. It's almost like you can get into the topic by learning the Diffie-Hellman method, but you will eventually have to learn a bit about discrete logs if you want to read
Sure.
research
Sure.
papers. And I think
Yeah.
maybe that's the reason that academics are doing so well in industry, because industry is lacking that formalization, ability to read research papers, especially.
Yeah. Yeah. And I think that's part of what a PhD and what an education in cryptography is supposed to be about, right? Learning these fundamentals, learning the different aspects, learning how to apply them to your research.
Yeah. I learnt a lot from the Handbook of Cryptography. I don't know if you use
Oh
that
yeah,
book, but I
sure,
spoke
sure.
to
Yeah.
Alfred Menez, and his big regret with the book is that he didn't cover elliptic curve cryptography. I think it
Right.
was around at the time,
Yeah, yeah.
but
Actually, this is an example of a book that's now a little bit out of date, right? It's actually was written about 30 years ago, 30 plus years ago,
yeah,
perhaps, right? And so it could stand to be updated, but I don't know. It's almost, the scope now of applied cryptography has become so large,
yeah,
it would really be difficult. I actually was approached a few years ago about trying to come up with a revised version or a new edition of such a book. And I just thought it was too complicated to do. The only way you
possible.
could really do it, I think, would be as some kind of an edited volume. where you
Yeah.
have people contribute chapters on their area of expertise. But my experience with edited volumes is that the quality doesn't tend to be so great because there's no
No.
unified notation and people
No.
are there's no relation between the chapters, and so I wasn't excited about doing that.
Yeah, I think there's a book on post-quantum cryptography that Daniel Bernstein wrote, which has some great chapters in it, but there are ones that don't quite
It's a
gel
mixed bag.
together.
It's a mixed bag,
And
right? Exactly.
yeah,
And there's just no cohesion between the chapters a lot of times.
yeah, that's right. Yeah. So if you were to teach a course on cryptography to computer science students, I know it's very difficult to define the level because it varies across different universities, different countries, and so on. But what would be the key topics that you would actually teach them? Let's say you've got a 12-week semester. What topics would you want to teach?
Yeah, I mean, I've done this obviously many times. There's sort of two types of I don't want to call it cryptography courses, but cryptography lectures that I've given. So first of all, I used to teach a general undergraduate computer security class, which had cryptography as a component. So there, it was meant to cover the breadth of computer security. And I would usually start out the semester by spending about 3 weeks or so on cryptography. And the goal there was not to give people any of the low level mathematics that they need to really understand what's going on under the hood in cryptography, but more to explain to them what cryptography can offer, to try to convey to them some of the security definitions that we use in cryptography. And then, just understand, well, if you pull this, algorithm off the shelf and use it as an encryption scheme, number one, this particular algorithm here is the one that's safe to use. And number two, here's what guarantees you're going to get. And be aware, for example, of like whether you need, in your particular scenario, whether you need security only against a passive adversary or whether you also need security against an active adversary. So that's kind of one thing. But then for a more specialized, class where people actually want to learn cryptography and want to get into the details. So, one thing I start out from the beginning, and we spoke about this before, is to try to convey to the students the importance of formal definitions and proofs of security. So, again, really understanding and trying to hammer home what these definitions are trying to accomplish and what definitions mean and why do we define things one way and not another way. And if you now want to use one cryptosystem as part of a larger system, what definitions do you need the underlying cryptosystem to satisfy in order to do that and things like that. And then going through the mechanics of the proofs themselves, right? Showing students how you can actually prove security of a cryptosystem based on an underlying assumption. So, I usually in the first lecture or two, I get to that. And then it's sort of standard. So, start out with one-time pad encryption and perfect secrecy and the limitations of that. Spend about half the semester on private key cryptography because it's really a workhorse for a lot of what happens in the real world. Private key encryption, message authentication, hashing, right? And you can get into all kinds of things already, all kinds of interesting things about definitions and how to satisfy the definitions and what you need to do and things like that. And then usually I'll spend a couple of lectures talking about how block ciphers are constructed in practice, kind of at a bit of a high level, right? Explaining the design principles for AES, for example, and going through that just to kind of show students a concrete example. I mean, what I do like is to kind of mix the theory and the foundational stuff with things that are actually used in practice. So I always try to tie things to that, and I always try to give students programming assignments that they can use to get a concrete sense for the theoretical topics we're talking about. And then moving on to public key crypto, and here it's a bit challenging because generally I can't assume that the students who are taking my class have had a background in number theory or algebra or things like that. So some of them come in really and they don't like the mathematics or they're scared of the mathematics. But you need to get through it, right? And so I spend a couple of weeks covering that and then move on to public key cryptography and digital signatures. And then usually save time for some advanced topics at the end. But it's a lot to get through. And one thing that's interesting also is just thinking about cryptography courses going forward. With the increasing importance of post-quantum cryptography, and especially with the recent announcements from NIST about post-quantum cryptography standards. It's going to be really important to cover that in cryptography survey courses, but I think it's going to be challenging for the students. Somehow or another, I feel like these lattice-based encryption schemes, for example, they're sort of inherently more complex in some ways than classical RSA cryptography or Elgamal encryption. And I do wonder. I actually, I have not taught a cryptography class at the undergraduate level that has really focused on post-quantum cryptography yet. And I sort of wonder how that will go for the students. I do think it'll be a little bit challenging for many of the undergraduates, but they're going to have to, learn it if they want to learn modern cryptography.
In speaking to some of the people who have been involved with the development of lattice cryptography, they typically will say that you need to look at uh, uh, Peter Shor's signature method and also the Fiat Shamir. I think if you teach that, then it doesn't become too difficult. If you just treat it like matrices and vectors and so on, and you add the noise and you can assume the noise doesn't have a large effect, then the maths actually boils down quite simply. So perhaps
Yeah,
there
I've
is.
heard that. I've heard that argument before, and yeah, I don't know. I mean, you're right on the one hand that lattice-based cryptography doesn't rely on anything more complicated than like you said, linear algebra and modular arithmetic, and in some sense, that's simpler than the group theory you need to learn for RSA. I do think that the presence of this noise, maybe it's just me because I grew up, not having noisy crypto systems, right? And maybe for students approaching it for the first time, it can be natural, but I feel like it complicates all the calculations, right? So every time with RSA, for example, you can do and you can give students an example of RSA with small parameters, right? You can work with n equals 21 and give them an example of RSA. It's a little bit harder to do that with lattice-based crypto systems because even to do anything interesting, you need, you can't use a 2 by 2 matrix and do anything interesting. You need to use a larger matrix. And then once you start adding noise, you already need to use a reasonably large value of Q just to make things work out. And it just becomes messy very quickly. But yeah, I conceptually it should be easier to teach than RSA.
Yeah. And I suppose with the hash-based methods, we have the Merkle tree,
Yeah.
and it's quite an interesting concept in actually again using more formal methods, more provable methods within the Sphinx plus method, but it ends up with very large signature
Yeah,
sizes.
and
But
again, the underlying ideas are simple and they've been around for since the 70s. But yet when you again, it's an instance of a crypto system where you can't work through an example on the board, right? A concrete example. I mean, you can
yeah,
draw the picture and etc. But you can't do a concrete example because you can't
yeah,
express a hash function on
yeah.
on 1 byte inputs or anything like that. But yeah, it's just a different mode of thinking or a different way of having the students learn that stuff. But I'm sure it can be done. I actually, since we were speaking about books before, I think there's still a need for a good undergraduate, let's say, level introduction to post-quantum cryptography. So maybe
Mm.
that'll be something that we'll see someday.
Yeah. And do you think there are any gaps in computer science courses when it comes to cryptography? I know that you probably teach in a certain way, but generally, do you see syllabuses missing things?
Yeah, I haven't looked recently, but I remember something that maybe happened about 10 years ago when I was looking at a book on I think it was operating systems, and they had a chapter or maybe a section about cryptography. And they were still talking about using textbook RSA encryption. And I think and it's not unique to that book. I think there are lots of instances in math departments. There are often math departments teaching cryptography, or when you have other systems-oriented courses within computer science using cryptography, like this operating systems example, where they just don't realize that textbook RSA encryption is number one, no good, and number two,
Mm.
we've moved on from that 30 years ago, and
Yeah.
and it's time to do something, teach something a little different. So from that point of view, I still do think that there are people sort of outside the core cryptography community who are not aware of how cryptography works. Um, but it's less and less. I think there are now more resources about cryptography, more people, more awareness about cryptography, that you see that, less and less. But you still do encounter that sometimes.
Yeah. And you've obviously worked
Or
in
the other thing
many.
that bothers me is when
Yeah.
people talk about what is it they say, you can create a digital signature by just decrypting something. And it's like,
No,
no, decrypting and signing are totally different. And
no,
maybe 40 years ago there was this idea that they were similar, but we've moved on since then.
no, that's right. And so you've worked in many areas of research, I think identity-based encryption, MPC, zero knowledge proofs, and blockchain methods. What is your favorite research topic?
Yeah, it's a good question. I mean, it changes from time to time. Maybe it depends on the problem I'm working on, but I think I am partial to protocols, and I guess probably MPC protocols, multi-party computation, and related things. It's interesting to think about, to reason about these protocols and to write proofs for these protocols, and I think they're also very very useful as well. So I appreciate the application of those also.
Yeah. And you've published in areas of predicate encryption. Can you outline what that is and how it's used?
Yeah, yeah, this is actually interesting. This was sort of an idea that I guess was proposed maybe 15 or 20 years ago, but has really become we've seen become a lot more powerful since then. If you think about sort of standard public key encryption, in standard public key encryption, you have one party holding who generates a public and a matching private key, and then anybody can encrypt to that party using the public key, and only the person with the private key can decrypt. Um, Predicate encryption kind of gives you a more powerful way of managing keys and using public key encryption for sending messages to a large number of people, only some of whom should have access. So let me kind of give you an example here. So the idea with predicate encryption is that you have now a single party generating a master public key and a master private key. And then they have the ability to use their master private key to basically give out what you can call delegated keys to different parties, where those delegated keys are associated with some predicate. Okay, and I'll give an example in a minute. But so now you can use this master private key to generate private keys corresponding to different predicates. Anybody can now encrypt using the master public key. And when they encrypt their message, they'll, alongside the message that they're encrypting, they'll also identify some attributes that they want to be associated with that ciphertext. And then the property is that any private key associated with some predicate can decrypt some ciphertext associated with some attributes if and only if the predicate evaluated on those attributes is true. Okay. So an example of this, and you mentioned IBE earlier. So IBE is kind of a simple example of a predicate encryption scheme where the predicate is going to be equality. So I can take my master public key, I can generate for you a predicate based on your email address, and then somebody can encrypt with the attribute being some email address, and you will be able to decrypt that only if your email address matches the one that they encrypted to. That's kind of a very simple notion of predicate encryption. You can imagine more general forms of predicate encryption where, I mean, the predicate in theory can be arbitrary. You can have predicates based on people's role within a company, predicates based on their email address, predicates based on what kinds of data they should be allowed to have access to. And so it gives you a really nice way of doing key management within a larger system. And I think there are some companies now trying to commercialize this idea and use it exactly for this purpose, whether it's within a company, within a large organization, or even for identity-based encryption as a particular example. It seems to be very useful from that point of view. And so the paper that I worked on back then was looking at constructing predicate encryption for a particular predicate. But like I said, there's been a lot of work since then on generalizing this, even generalizing it further to something called functional encryption, where so predicate encryption essentially tells you, either you can decrypt or not. Functional encryption even goes beyond that and says not only, can you potentially decrypt or not, you might only be able to decrypt and see part of a message rather than the entire message, or more generally, some function of the message rather than the message itself. And so that's also something people have explored a lot since then.
And could you apply it to location and time? Because those are two of the most important attributes. Like if I need to make sure that you can only read the email in London and only within a certain time, is it? And
Yeah, that's
they're
interesting.
difficult
That's an interesting
attributes.
idea. So to some extent, you can apply it to time. I'll tell you how. There's a notion called forward secure public key encryption,
Mhm.
which then also was further developed since then. But the idea there is that I have a public key, and I have a private key. And what I'll do though is I'll every night at midnight say I'll update my public key for the next day. And so somebody can now send me an encrypted email, and I will be able to decrypt it. Let's see. So they'll send me an email associated with a particular time period. Let's just take your example and say they want me to read it today, and I will be able to read it to decrypt it using my current key today and read it. But once I update my key to the next day and delete the previous key, I can no longer read it. Now, obviously, it's a
I
little
see.
different from what you're talking about because here you're
Mm.
trusting me to delete my old key. And the reason I
Yeah.
would do that is because I might be worried about somebody compromising my machine and learning my key. And if so, I don't want them to learn, all my previously decrypted emails. Um, but in the scenario you're talking about, it's a little more challenging because I think there you don't even trust the recipient. And so if the recipient may not delete their key, then it becomes a bit more challenging. You need to worry about revocation. You need to worry about maybe the authority will only hand out a key for a particular day at midnight on that day, and then I have to worry about proving that I'm in a particular location, etc. But yeah, that's an interesting idea actually. I'd have to think more about it, but you could certainly imagine doing something like that if everyone's trustworthy, right? If everyone is trusted to delete their key at a certain
Yeah.
time and accurately report their location to this authority, you might be able to do
Yeah.
that.
Yeah. I mean, obviously, it's a really difficult topic, and a company like Google needs to make sure that they've actually deleted something. So actually showing a proof of deletion is a really difficult task that you've deleted
Proof
the
of
data
deletion is
everywhere.
is very difficult. In some sense, it's impossible, right? If you
Yeah.
have classical information, you can never really prove you deleted it. Interesting, one way that so this is again based on a trust assumption, but one easy way to delete data is to encrypt the data and then delete the key, right?
Yeah.
And then you only have to worry about proving or convincing somebody that you actually deleted the short piece of information, and then they know you can no longer access the original information. One thing I'll mention though is that with quantum information, there are now a bunch of proposals of schemes that do allow you to prove that you deleted quantum information. And there you can
Yeah.
actually do this because, fundamentally, quantum information in general can't be copied. And so you don't have the same problems or the same impossibility results that you have with classical information. So maybe with quantum you can do something like what you're suggesting.
Yeah, I did see a research paper with a one-time signature in a quantum machine, and
Yeah.
the private key never exists anywhere, and that's something that you couldn't do in a classical cryptography setting.
Yeah. Yeah.
So there's one area of cryptography that I've always struggled with. I understand most of the areas, but garbled circuits are a real blind spot for me. Could you just outline what they are, how they're used, and
Yeah.
what problem they address?
Yeah, yeah. Garbled circuits are a key technique that's used in secure computation and mostly in secure two-party computation. Um, the way to think about it is that you have two parties want to do a secure computation involving a circuit that they both agree on. And what one party can do is they can take the circuit and they can garble it, as you said, and generate a garbled circuit corresponding to that underlying circuit. And essentially, what they can then do is they can set things up so that they can send that garbled circuit to the other party. And as part of that process, this party will also kind of embed their own inputs into that circuit in a garbled way also, so that the other party can't tell what those inputs are. And then the second party can go ahead and essentially evaluate that garbled circuit and get a plain text result at the end. So this gives you yeah, a way to basically allow those parties to evaluate a circuit without either party revealing their inputs to the other. And I guess at some point, yeah, I'm happy to explain it more technically if you want. It's actually pretty it's developed to the point now where it's become I would say fairly straightforward as these things go. There've been a lot of optimizations where those start getting more and more complicated. But I think the basic idea it relies only on encryption, symmetric key encryption, and so from that point of view, it's pretty clean. Yeah, so well, anyway, I'll leave it there. It's hard to explain without a whiteboard, but
Yeah,
it is kind of a nice technique. One thing I'll mention is that it's like it's a little different. Well, it's actually very different, I would say, from something that sounds like it should be related, but it really is very different, which is obfuscation.
Mm.
So when you obfuscate a circuit, it means you hand the circuit over, or an obfuscated version of the circuit over to somebody else, and they can then evaluate that repeatedly on any inputs of their choice. So they can't see the internal workings of the circuit, but they can, evaluate the circuit on any input X and get the output Y. A garbled circuit is a little different. First of all, you can only evaluate it once. You can't evaluate it multiple times. And the other fundamental, and the reason for that actually is because if you give me a garbled circuit, I actually can't evaluate it on my own without some additional help from you. And that additional help is essentially I take my clear text input that I want to evaluate the circuit on, and then I run a protocol with you that allows me to get some keys that correspond to my input. And then using those keys, I can go ahead and evaluate the circuit. And that's really, I guess, the fundamental difference between that and obfuscation. Whereas for obfuscation, I can evaluate the circuit on my own. For a garbled circuit, I need your help in order to evaluate it on an input.
That's really interesting.
Yeah.
And I read a paper the other day, and it was related to a covert channel within an LLM where it was possible to create two keys. One key will encrypt the secret message, and then it's possible to convert that into an English character type format. And then the second key is then used to place the characters within a story that's generated by an LLM. And this was a way to create a covert channel. I know that they've been around for many years. So I like your work because you have that crossover between AI and cryptography. And I think you've published on watermarking of LLMs. And that's such a big topic, especially in academia and education just now. So could you just outline how it's possible to watermark LLMs?
Yeah. The basic idea is actually pretty simple. So first of all, let's think at a high level about what an LLM is doing. So essentially, you give an LLM a prompt, and based on the prompt, it generates some kind of a probabilistic model of what the next token should be following the prompt that you gave it. And then it repeatedly does that, right? So it generates, some probability distribution for what the next token should be, and it chooses one of them according to that probability distribution. And then based on that, it updates its table of probability distributions and figures out what the next token should be, and et cetera. And kind of the observation we had in that work is that what you could do is you can take this table of probabilities of what the next token should be. And if you imagine, looking at that table and then picking things from the table, not only according to the probabilities that are there, but also based on some secret key. So just as a simple example, maybe I have some secret key and I evaluate it on every token in this list of possible tokens. And some of them are mapped to a 0, which means I cross them off the list. And some of them are mapped to a 1, which means I'll allow them to be retained as possibilities. And then I only pick the next token based on the possibilities that are remaining. So essentially, the next token I pick in this case is going to be guaranteed to be something on which my privately keyed pseudorandom function evaluates to 1. And then I do that for the next 100 tokens. Okay. So now what you can see is that the probability that somebody is going to generate a string such that the pseudorandom function evaluates to 1 on all next 100 tokens is going to be exponentially small. But I'm doing it, guaranteed with 100% probability. So if I can reveal the key afterward, for example, then somebody could verify that I indeed was the one who generated that 100 token string. Or if I'm in a scenario where I want to keep the key private to myself, I could look at the text that somebody gives me. I could evaluate the pseudorandom function myself, and then I could know myself that yes, this was something I generated, or no, this probably wasn't something I generated. So that was the idea there, basically. And yeah, I think that the idea is actually a pretty powerful one because, like you said, people are interested in well, in watermarking the models that they're developing. I mean, we know that people are now very worried about the provenance of the models and what happens to the models after they release them. And this potentially gives a way for people to, put a stamp on the model that they put out, or the model that they're using, I should say, and then show that anything generated, did or did not come from that model. I mean, I should mention one of the challenges we had, right, is that in the way I described it, it's really only privately verifiable. So if I release the key, then anybody could come up with quote unquote watermark text. So extending that work and making it, having it work in this public watermarking setting is much more challenging, and it may even be impossible, actually.
And does it degrade the performance of the
Oh yeah,
of the information?
Right, that's a great question. Yeah, so it is a concern that right, in this mechanism I described, right, you might take the most likely token on the list and you might cross it out, and then you're degrading the quality of the model. And so, first of all, there are ways to account for that. Just as a simple example, right, if something does have a very high probability, then maybe you actually, you skip that token and you go to the next token. But it does degrade, but we showed it actually only degrades by a little bit. So it really doesn't affect the performance that much. And I guess one reason for that is that in general, when you give a prompt to an LLM, there are many, many possible tokens that can extend that prompt. Some of them might be even direct synonyms for each other. And so it doesn't really matter much whether you use a word A or word B if they mean the same thing. And so you have a lot of flexibility without degrading the quality of the model too much.
So the application is less to do with, say, Google Gemini against OpenAI, ChatGPT. It's more likely to be individuals and organizations creating their own models and to be able to detect when those models have happened rather than the big companies actually detecting their own
Google actually
LLMs.
is using they are using watermarking for their models. It's not the scheme that we develop, but they are using a watermarking system for some of their models. I think it's really the real distinction I think is between models that are being publicly released, because once you publicly release a model, anybody can use it. Whether or not you detect it after the fact is another matter. Or versus these kind of closed source models where the model is not publicly released, but you allow people to have access to it, whether it's a paid service or not. And then you might be worried about people, interacting with your model, getting some response, and then I don't know, publishing a book based on it or something like that. So I guess those are two different scenarios to distinguish. And when people are releasing open source models, I guess they pretty much expect that people will take them and modify them and do what they want with them. The genie's out of the box. There's not much you can do. So it's probably the watermarking is probably more of interest for these closed source models.
Okay, and there hasn't really been much advancement on encrypting the model at all. I know that can be done with the homomorphic encryption in neural networks, but the performance goes through the floor.
Yeah, that's a great research direction, and there are different ways you can imagine trying to tackle that question. But like you said, it is really challenging. I think even with homomorphic encryption, well, okay, so what you'd really want, and this goes back to our discussion before, is you really want an obfuscation of the model because you want, let's say, well, it depends what you're trying to do, but if you want to allow people to run the model on inputs of their choice, but not learn the weights of the model, then that's one way you would do it. Interestingly, there's been a line of work showing that this is not, in full generality, not really possible. Some work by Adi Shamir, actually, where they apply tools from cryptanalysis to these models. And they show that basically, even if you only give me, allow me to give inputs and get outputs from the model, I can gradually learn the weights of the model itself just by giving it certain inputs and looking at how they change the output. So there's some inherent limitations on what can be done there. But yeah, trying to apply ideas like obfuscation or fully homomorphic encryption to get some benefit would be really interesting, but it seems super slow right now.
That's right, yeah. And you've also worked in zero knowledge proofs for training within neural networks. Could you just outline how they work?
Yeah, so the problem we looked at there was it was another example of trying to apply cryptography to machine learning. The problem we were considering there was basically how can you convince somebody that some model that you release was actually trained correctly on some specified data. And what we imagine there is that the person doing the training has committed to their data in advance, so they don't have to reveal it publicly. They can just reveal a commitment to that data. And they've also committed to the mechanism or the algorithm they're going to use to train their model based on that data. And then we basically go ahead and use one of these zero knowledge snarks that we talked about earlier after they ran the training algorithm, they were able to prove that they correctly ran that algorithm. And they can publish a relatively short proof of that fact that anybody can then go ahead and verify and thereby become convinced that the model that they see it was actually trained according to some prescribed mechanism on some committed data. And there were some challenges there in terms of the scale of what we were trying to do and trying to use the right proof systems and using incremental proofs in the right way in order to make this feasible. But unfortunately, even with all of that, it's still probably a bit too slow to be used commercially now. But maybe with further advancements, that would be something, or different ideas altogether. That might be something that people would adopt one day. Because I think it's a concern nowadays is that people, there are all these models out there, and nobody really knows in the end of the day, how they were trained, what data they were trained on, et cetera. And so it would be nice to be able to provide people with this kind of a proof of the integrity of the model.
Yeah, I think if you ask many of the leading researchers in cryptography, they will say that's the area that we need to work more on, that proof of computation, almost the formal proof that something has went through a certain process. And I think for machine learning and AI, it's becoming increasingly important that we actually prove the provenance of the data that went in. And obviously for Google, this is an important area.
Yeah, for sure. And I think that, it even goes beyond that. It goes a little bit beyond the cryptography because just understanding where the training data comes from is really super important. And we know there's all kinds of attacks you can play, whether they're directed attacks against a particular training algorithm or whether they're just by polluting the internet with garbage data that this AI is going to scrape up. And so like I said, that goes even beyond the cryptography because you have to understand what kind of data you want to train on to begin with. And you need to maybe do some filtering to make sure you're only training on quote unquote good data. This is a complicated space, but one that, like you said, is going to be really important.
Yeah. And I know that Apple have done a lot of work on their secure clouds. They've been using homomorphic encryption and searchable encryption, which allows them not to know what a user is actually searching for, but still deliver content. I think you worked in this area. Can you say what the core applications of this type of technology would be?
Yeah, I mean, in the general level, it's exactly what you said. You could imagine. I mean, and I even saw this in some early talks on fully homomorphic encryption. Right? You could imagine having an entirely encrypted search where I send some encrypted search term and and through the magic of fully homomorphic encryption, you could then match that search term with the entire search index that you have stored and return the results to me without the other party learning anything about what terms I was searching for. If you think through it a little bit, I mean, in that level of generality, it's completely infeasible. One of the limitations there is that if you really want to hide everything about the search term, then in particular, you need to hide the number of results you're returning because the number of results already leaks information about the search term. And once you're hiding the number of results you're returning, that essentially, there are different ways you can frame this problem, but essentially it means you have to pad the results you return up to the maximum number you're ever going to return for any search. So that means that even if I'm searching for a relatively rare term, you're going to have to return me as results of size equal to the most popular search term. which kind of makes this infeasible. But you could imagine applying this idea in more limited domains. So, maybe rather than thinking on the scale of a Google search, you can think on the scale of, searching some pre-processed corpus of my emails, for example, for keywords. And then it's a much more, narrow domain. There's a much more limited set of keywords that I have to worry about. Maybe there's a lower, a reasonable upper bound on the maximum number of emails that will ever match any keyword. And there have been a lot of interesting proposals there. There are some companies actually trying to productize this and use it in the context of database search. And yeah, it's another example of a privacy preserving tool trying to ensure that users still have privacy even as they're trying to get the benefits of relying on all these companies out there giving them data. So
That's great. Yeah. And obviously the Diffie-Hellman method, so you learn the Diffie-Hellman method and then you're told that it's weak because we can have Eve in the middle and it will break. And then we need a digital signature on the top of that to make sure that we authenticate. And we're only authenticating on the internet one way, on the server. So there's been a big rise in authenticated key exchange, AKE, and in areas like PAKE, password authenticated key exchange. And I think you worked on a system that related to human memorable passwords. Could you just outline what that was?
yeah, that was work that I did back as part of my PhD thesis, and it was really interesting because, like you were saying, the typical way that we do authentication now over the internet is server to client only. Okay, it's more complicated than that, but at a high level, right? The server has some public key. We have a public key infrastructure set up behind the scenes, and a client can verify, say that they're talking to Amazon by checking that the server that they're talking to is able to sign things under the key that's been that Amazon that Amazon has. I mean, it's obviously very complicated because you have a whole PKI behind it, but that's the general idea. And the question we were looking at in that work was to what extent you could have mutual authentication based only on a common shared password. So think, like a typical client-server model where the client knows a password and the server knows what the user's password is. And how can you bootstrap an authenticated channel based only on that? And there's a couple of interesting kind of conceptual challenges there. I think one of the things is that, you want, at the end of the day, cryptographic security. But you're limited by the fact that the password is likely going to be short and going to be low entropy. So somehow you want to bootstrap a channel that's going to have the equivalent, say, of 128-bit security, but you're doing that starting from only, I don't know, a 20 bits of entropy password. So fundamentally, there seems to be an issue there. And the related to that, well, is the fact that an adversary who's trying to guess your password can certainly do that with at least 1 over 2 to the 20 probability in this example. Or if they, make 2 to the 20 online attempts, they'll eventually hit on your password and be able to break it. So fundamentally, there's something at odds there, and that becomes interesting in terms of how you frame the definition. So, unlike typical cryptographic definitions that require the attacker's success probability to be negligible, in these definitions, essentially you have to allow the adversary to succeed with non-negligible probability, but you don't want it to succeed with probability any better than the number of online impersonation attempts it makes divided by the size of the password dictionary. So that's challenging. And then to achieve that, you have to make sure essentially that the attacker can't do what are called these offline dictionary attacks, where it eavesdrops on an execution of the protocol, and then based on that transcript tries to figure out what the password is. So those should be ruled out. Otherwise, it would be trivial to break any protocol. So this made it really challenging to come up with a protocol. Yeah, there at the time I was working on this, there were a couple of papers that came out that were really sort of inspirational for me in thinking about the problem. And then we were able to develop our own solution that based essentially on some variant of Elgamal encryption actually, but wrapped up in a lot of other things. So that was actually a lot of fun to work on back then. And I'm happy to see now that there's been a lot of progress recently on password authenticated key exchange, and some standards actually came out relatively recently, and people seem to be keen on adopting them. So that's really nice to see.
That's great. And I think you recently published a paper on round optimal fully secure distributed key generation, or DKG. How does that work, and what are the
Yeah,
applications?
that's it's going to be hard to explain how it works, but I think just at a high level, what I would say is that it that came out of this work I was doing for a startup company that was looking at using threshold signatures to to allow people to better protect their crypto wallets. And we were really just interested fundamentally in the question of how many rounds you need in order to get fully secure DKG. And turned out to be a really interesting problem, really interesting to think about, and interesting also because the answers that we got, or that I got in that paper, depend a lot on what you're willing to assume. So what you're willing to assume in terms of prior setup, what you're willing to assume in terms of cryptographic hardness assumptions. And there's still a lot of open questions there, actually, doing it from minimal assumptions and understanding what the round complexity is there. But that was a really fun project that came out of that work.
Yeah, because a lot of this goes back to the verifiable secret shares, the Feldman
Yeah.
Peterson type systems where you
Yeah,
don't
exactly.
actually
Again,
have it.
another example of these classical ideas that from the 90s in this case, right, that then turn out to have these amazing applications in all kinds of crypto systems.
That's right. And obviously the dealer could go bad in a lot of these systems. So I think
Yeah,
they,
exactly. So I mean, since you're asking a little bit about the technical details, one of the techniques we have there is essentially, you have a set of N parties who are running this DKG, and each of the parties will act as a dealer in one of these verifiable secret sharing schemes. And then you have some detection mechanism in case one of those parties is trying to behave maliciously. And then the guarantee is that you have a sufficient number of parties who are honest, and from those honest parties, you can recover a key. So yeah, that's very interesting.
yeah, because I've seen research that allows you to be able to discover the bad actor and to revoke their part of the share, and then everyone else can regenerate the shares. So no one has to regenerate the private key
Yeah,
again, and the private key never really exists, and so on.
yeah,
So
yeah.
some really interesting work in that
Yeah,
area.
so the trick is to do that in like one or two rounds, right? So you can easily see how you might be able to do that in three or four or five rounds. You detect, and then if you kick somebody out, and then you run it again. It's hard to compress that and do it in a small number of rounds.
So multi-party computation is a growing area of research at the current time. What's your core ideas on creating an MPC system that can be trusted and is secure?
Yeah, that's a great question. I mean, we've seen a lot of work on MPC within the academic community over the last several years, really improving the efficiency quite a lot. And there's now even a whole bunch of open source libraries that you can use for MPC. But except for a couple of special purpose MPC protocols, we haven't really seen wide adoption of these protocols in industry. But I still think that actually there is a lot of benefit to be gained even from these special purpose protocols. And I'll just mention one example that's kind of top of my mind since we were just talking about threshold signatures. You can view a lot of the work on threshold cryptography as being a special purpose multi-party computation. What you have there is you have some number of parties who all have secret shares of a key, and the functionality they want to compute is to combine all those key shares and recover the key and then generate a signature using that key. And so that's an amazing application that even though it's not generic MPC, is hugely beneficial and being used by several companies. And so you can get a lot of benefit by looking for the right use cases where you can apply MPC. Probably that's the direction I think things are going to go. Even when you have general purpose MPC systems, the parties involved are not likely to be running an MPC on completely arbitrary circuits that change every day. There's likely to be some small set of predefined types of circuits that they're going to be interested in running on, depending on the domain that they're working in. And so you can then try to optimize your MPC protocol for circuits of that form. And I think that it's still, it's the kind of thing where I think if more people knew about it, they would see more applications for it. I can imagine that there are lots of instances where people are trying to solve some problem, they can't share their data. And if they only knew about what was available to them, then they might be able to think of a solution using a multi-party computation. And maybe that's partly telling us that we need to do a better job educating people about what's available.
That's great. And my last question is, what does the next decade look like in cryptography? Obviously, working in Google, you can actually see the horizon. What are the big problems to be worked on? What does that next decade look like?
And I mean, first of all, I would say it's a very exciting time. With the with the NIST standardization process just wrapping up, it's still actually ongoing in terms of additional schemes that they're considering. NIST is also right now looking for proposals for threshold crypto systems. We talked earlier about the huge number of companies in the startup space, cryptocurrencies, zero knowledge proofs, etc. It's really a great time for cryptography. It's like almost a renaissance, I think, for cryptography right now. It seems that the one of the biggest domains where cryptography can be helpful, I think, is with regard to ML and AI. Right now, I think we're seeing the power of these ML systems kind of outstrip the safety that we can put in place around them, and concerns about privacy, concerns about malicious tampering with models and things like that. I think cryptography has a real role to play there, and it's going to be only more important in the decade to come.
Yeah, I agree completely. I think if you drew a Venn diagram of AI and cryptography, the sweet spot is where they meet in the middle.
Yeah.
So thank you so much for taking up your
This was a real pleasure.
precious
Thank you for inviting me.
Thank you. Okay, keep up the great work. Thank you.
Yeah, thanks. Yeah, thanks again, by the way. It was really, I appreciate it.